Hi students, hope you all are doing well. So, let us move on to Module 3 Software Vulnerabilities. The contents of this module are buffer overflow vulnerability, which is mainly of two types: vulnerabilities related to stack overflow and those related to heap overflow. After that, we'll be seeing cross site scripting, SQL injection, and then phishing. What do you mean by software vulnerability, or how do we define it? Software vulnerability is a glitch, flaw, or weakness present in the software or in the OS. Or, in other words, we can say that they are the unfortunate loopholes that exist in the software, which could be exploited by some attacker. A piece of software is insecure if cleverly designed inputs can cause some harm to the system in which it gets executed. Of course, such systems must be taking some input from the user. Then only this can happen, because it is along with these inputs the attacker injects the malicious code. The different types of software vulnerabilities include memory safety violations. These type of vulnerabilities exist in systems where memory usage by programs is not strictly monitored or restricted. Buffer overflow is one such type. The next category are those that exist due to improper input validation. These are usually seen in web based applications that accept some input from the users. Examples are cross site scripting and SQL injection. Apart from the system or software imperfections, vulnerabilities also exist due to careless human behavior. Attackers are well aware about this and they exploit it in many ways. Phishing attack is an example of this type. Actually, there are many more types of software vulnerabilities that you should be knowing, but our syllabus limits us to these few types. Buffer overflow vulnerability is the oldest and the most common type of vulnerability that has been exploited. In 1988, the Morris worm attack, the first major attack on the internet, was launched by exploiting BOF. It resulted in distributed denial of service across the entire network. BOF occurs when the space allocated for a variable becomes insufficient to contain the value of the variable. This happens as programs do not perform array bound checking while accepting inputs. Buffer is an area in memory that stores data temporarily, usually in the main memory, that is RAM. A program that uses a buffer is considered to be a vulnerable program, as the buffer cannot be trusted. Why do we say that the buffer cannot be trusted? Because these buffers got a habit of leaking their contents to the physically neighboring locations whenever the data given to them is larger than they can hold. Attackers exploit this and design inputs so as to cause buffer overflows in the way they desire. This vulnerability can create an entry point for a cyber attacker whereby he can launch any attack that can even lead the system to crash. Why does this buffer overflow occur? Because in languages like C and C++, there are certain functions that accept data without being aware about the amount of memory allocated to them. For example, the function gets reads a string from an IO stream until it finds a new line character, not until its buffer gets full. Hence, Software developed using C and C++ are more susceptible to buffer overflows. However, other programming languages are free from such buffer overflow vulnerabilities. BOF is also platform specific. That means a program that is vulnerable in one system may not be so in another system because of the difference in the processor or the operating system or both. Now, let me explain to you how BOF occurs using a simple example. Consider the portion of code written in C. Here, a character array A of size 8 is declared and initialized as a null string. Hence, 8 bytes would be allocated for it in memory. Remember that the C compiler automatically places a null character at the end of every string. Hence, while declaring the size, space for the null character must also be considered by the user. The variable b is declared to be of type unsigned short int, which requires 2 bytes and has been initialized with the value 1979. The table shows the contents of memory after executing the above two instructions. As you can see, the variable a has been allocated 8 bytes. The values in those 8 bytes are all zeros to indicate the empty string. And the variable b has been allocated 2 bytes. The binary equivalent of 1979 will be stored in those two locations. Their hexadecimal notation has been used for convenience. Now, suppose that the next instruction is a string copying function, strcpy. String copy a, excessive. Here, the first string is mentioned as a character array variable and the second string as a string constant. So, the second string is to be copied into the variable a. The second string contains 9 alphabets plus 1 null character. Hence, it requires 10 bytes of memory. The 8 bytes would be taken from the location allocated for a, and next 2 bytes would be taken from the physically neighboring location. Unfortunately, the space where the value of b was stored. This is how a buffer overflow happens. As a result, the value of b is lost, as it has been overwritten by the last 2 bytes of the copied string. Now, before going into the details of Stack Overflow, let's recall some points regarding memory organization. We know that the main memory is divided into different segments, usually 4. The different segments are reserved to store different types of data. The code segment is the portion of memory where the program code resides. All the input and output data of the currently executing program will be stored in the data segment. The stack segment is used whenever a function is called. The value of the local variables, the return address, and other information regarding the called function will be stored in the stack segment. The extra segment is usually used as another data segment. We know that the CPU has got a number of registers for easy access of data and address. Some of the address registers are instruction pointer or program counter. This register always stores the address of the next instruction to be executed. Stack pointer. This one stores the address of the topmost element of the stack. Frame pointer. Every function is allocated with a stack frame within the stack segment. Starting address of the frame of the currently executing function will be stored in the frame pointer. We know that stack is a data structure that works by the last in first out principle. It is an area within the stack segment of the memory where details related to a function are stored. When a function calls another function, the parameters of the function call and the return address are stored within the stack frame of the calling function. A new stack frame is allocated for the called function to save the previous value of the frame pointer as well as the values of its own local variables. When the call function returns, values are popped from the stack to restore the state of the calling function. Stack grows opposite to the direction of memory. That means data items are placed into the memory locations in the increasing order of memory addresses, whereas data items are placed into a stack in the decreasing order of memory addresses. That means an item at the top of the stack will have an address whose value is lesser than that of the item just below it. Now, let's see how a stack overflows. Consider the functions a and b. The green dotted area indicates a portion of the stack segment. FP and SP are CPU registers. We can see how the contents of these registers change as the program execution progresses, as well as how the elements are being pushed onto the stack. When function A calls function B, value of its local variables, parameters of the function call, and the return address are pushed onto the stack. The red block here indicates the stack frame of function A. The starting address of this frame, that is 8732, is stored in FP until B starts executing. Once program control goes to function B, the previous value of FP is pushed to the stack and the new value, that is starting address of the stack frame of B 8720, is returned to FP. The blue block indicates stack frame of function B. It stores the local variables of B. B has a character array which can store a maximum of 99 characters, one being reserved for the null character. A buffer of size 100 is reserved in the stack segment to store the array characters. The point to be noted is that the elements of the buffer are stored in a direction opposite to that of the stack. So, when a buffer overflow happens within the stack, the value of the local variables which are immediately beneath the buffer gets overwritten. If the buffer overflows further, the return address of the previous function will also get overwritten. This happens when the user enters a name with more than 99 characters. This is possible because the function gets do not check the size of the user input. This vulnerability of buffers is known to all. Hence, attackers design inputs so as to make the buffer overflow and rewrite the return address of the previous function with the one intended by them, so that when function B returns, instead of resuming function A, the attacker's code is executed. This is how a stack overflow gets exploited. Attackers who exploit stack overflows can do it in two ways, either by injecting a shellcode or by using an existing library function. A shellcode is a small piece of code used as the payload in the exploitation of software vulnerabilities. This sort of attacks are referred to as shellcode, as it starts by spawning shell programs. Shell programs are the means to access operating system services. If the targeted vulnerable program has root privileges, then root shell programs are spawned. Usually, the child process will have all privileges of the parent process. In order to manipulate files and folders, the attacker invokes system calls within the shell code. Every system call has a number and a purpose associated with it. Parameters of the system call are placed into appropriate registers before the call is executed. Let's see how a system call is invoked in Linux. For Linux running on an Intel 8086 processor, the system call execute VE is used to spawn a shell whose number is 11. The code for calling it is shown in hexadecimal notation. The value 11 is copied to register EAX and the software interrupt 80 is invoked. The system call execute VE has three arguments. The first one is the file name or path name which contains the executable, usually a binary executable or a script. The second one is a vector of strings, which is similar to the second argument of our main function in any C program. And the third one is a vector of strings, which are the environmental parameters like the root directory, etc. The system call replaces image of the calling process by the new process. The new process will have the same ID as the calling process. The system call returns nothing upon success, but a -1 upon failure. How the shell code is launched. The shell code designed by the attacker is given as the array input. The code is injected into a location whose address has been deduced by the attacker. The contents of the buffer is made to overflow in such a way that the starting address of the injected code gets exactly placed at the location where the return address of the function is stored. For this, the attacker makes a pre-study about the program stack locations of the system memory. Though not easy, by continuous experiments, attacker can get to know about these memory addresses. The animated picture illustrates how a shellcode gets injected. Function B takes the array input from the user. The shellcode is provided as the input, which gets located at the address 8207. The buffer overflows and finally the value 8207 gets returned into the location where the return address of function A was stored. As a result, when function B returns, the shell code starts executing and the attacker takes control over the system. If our stack has been made non-executable, then the attacker cannot run the shellcode from the stack. But they can still attack on us by using other options that do not require running of any code from the stack. One such attack is return to libc. Here, the attacker need not create any shellcode. He just needs to use some existing library function to spawn a shell. We know that C has a rich set of library functions. The starting address of these functions can be easily determined by anyone. In order to spawn a shell, the attacker merely needs to call the function system with the argument /bin/sh. The attacker may also call the function exit so as to terminate the program in a normal way. To get it done, the attacker just needs to do three things. He designs the input to the buffer in such a way that the buffer overflows and overrides the return address of the function with the starting address of the function system. Secondly, he places the starting address of the function exit just below such that the stack pointer points to it after the execution of the function system. Finally, he places the arguments of the function system just below the starting address of the exit function so that the function system takes this string as its argument. The animated picture shows how the input is provided and what kind of data overflows from the buffer and the locations where they finally get placed. After the function system gets executed, the stack pointer points to the function exit. The major reason for stack overflow is that many of the standard library functions do not check whether the target arrays are big enough to hold the content provided to them. Again, this is because the pointers don't carry length information about the entity they point to. Again, trouble comes because of the strings. The strings are all null terminated. Length isn't available without traversing them. Defense against BOF. Preventive measures can be adopted at various levels: programming level, operating system level, the compiler level, or hardware level. Preventive measures. Now, at the programming level, we can use a different language other than C and C++ in order to avoid buffer overflows, say Java, C Sharp, etc. Otherwise, we can avoid the use of risky functions like string copy, sprintf, etc. Instead, use their safe counterparts. Or else, we must get our code audited periodically to ensure that software vulnerabilities do not exist. At the operating system level, we can go for one that do not permit execution within the stack. That is, any code written within the stack segment is never executed. The content of stack are merely considered as data. Another possible solution is to randomize memory layout so that attackers cannot deduce any information regarding memory addresses. At the compiler level, we can choose compilers that uses canary. Canaries are values placed between a buffer and the control data to monitor buffer overflows within a stack, such that when the buffer overflows, the first data to be corrupted will be that of the canary. A failed verification of the canary data will therefore alert an overflow, which can then be handled. Or we can use safe compilers or safe libraries that check memory accesses at runtime. At the hardware level, we can choose to store the return address of the functions in CPU registers instead of RAM so that attackers cannot rewrite them.